So good afternoon. Should talk into this, I guess. Okay, so metathesis. What's olefin metathesis for the non-chemist? So we'll do a few minutes and then I'll tell you, you can, okay. So it turns out that what we do in organic chemistry is we make organic molecules, and organic molecules are made of carbon and hydrogen and lots of other things. And so this crazy reaction, which I first found out about at Stanford. So a group meeting with Jim Coleman, he came back from a consulting trip from Phillips Petroleum and said, I just heard about this really crazy reaction. It takes propylene and turns it into ethylene and 2-butene. So for non-chemists, it's 3 carbons into 2 carbons and 4 carbons. And by that stage, they knew it involved breaking the carbon-carbon double bind. So I had been trained as an organic chemist, and my area of interest was mechanisms, how organic compounds undergo reactions. And this reaction, we had no idea how it happened. So that night in group meeting, we started talking about the mechanism. We started talking about how the reaction happened. And then when I started my independent career, the first project I worked on was how this reaction proceeded. So I started doing this chemistry just because I couldn't understand it. And so we spent a lot of time working on mechanisms, but then a mechanism was proposed by a Frenchman, Yves Chauvin, who proposed a very interesting complex. So this is a transition metal, and 2 bonds to carbon, and then an R group. So we got blue R groups and red R groups. We'll see what these are later. And so the reaction he proposed went from metal carbon double bond to 4-membered rings. And you see this is now pseudo-symmetrical, so you can cleave this way and go back to starting material, or if you cleave that way, now you couple a red and blue, and you make a red metal carbon double bond. Now you bring in blue, and you keep going, and you can make everything shuffled. So that was the deal. And so the key to this then is the metal carbon double bonded species. And so once we knew the mechanism, then we could start to explore it. When we first started working on this, the catalysts were made by mixing a bunch of stuff together. We had no idea what was happening. We had no idea what the complex was, what the mechanism was, what was happening. And so once we had an idea about the mechanism, and we were involved in a lot of the work here, is that we could now start to try to make compounds like that to see if they would work as catalyst. So this is something for the people on the front row. and so it turns out that the Nobel Committee got very excited about this reaction, and they called it a molecular dance. And they even did a dance on the stage, apparently. I haven't looked at it. I've been told they got it wrong, but that's okay. So a lot of people did dances, but this one was done by a friend of mine, East van Harvath, in Hungary. And he was approached by national television and said, can you do a demonstration of what this year's Nobel Prize is all about? So he sent me some slides, and then I've got a lousy reproduction. So this is the metal, the lady in black, okay, double bonded to a carbon, okay? So these are all carbon pieces. And so then they proceed, and so now the lady in black and the lady in orange, and so you see these are carbon-carbon double bonds. They're holding 2 hands, okay? So there's blues and there's reds. So now the red has interacted with these. They make a 4-membered ring. So then they just split here. And then they have the lady in black with the red, and now the blue comes in. And you keep doing this, and it makes everything happen, okay? So this maybe will work. Here we go. So this is the lady in black. So the quality's not so good. Apologize, but there she is dancing around, and has to show off. And so now she's double bonded to that, and now you see these are the carbon-carbon double bonds dancing around, and then here comes a transition state, forms a 4-membered ring, then it cleaves, now double bond again. So you just keep doing that, and you've shuffled everything. So it's really easy to show how this reaction happens. Here comes another one, and around you go, okay? So it's like an American square dance, changing partners. But it turns out the lady in black is always the one who's involved in the thing. So that's the metal complex, and that's the catalyst. So she's always involved, and that's how it happens, okay? So that's the reaction, and you get an idea of how it happens. So the question is, what can you do with this reaction? So if it just made propylene turned it into ethylene into butene, that wouldn't be very useful. Except now that actually happens on a fairly large scale in industry. And there's reactions where people take C4 with ethylene and make propylene again. So it turns out this reaction goes back and forth. And what they do now is when they need C3, they mix C4 with C2 and make C3. When they need C2 and C4, they start with C3 and do the other way. So it's a way for the petroleum industry to re-equilibrate everything. So that's what the catalyst was used for before. When we started working on this, it only worked with hydrocarbons. But I'll show you later now we can do with many things, and so you can do cross metathesis, you can do ring opening cross, you can make rings, you can open rings and make polymers. And so you can make all kinds of different structures using this chemistry. And it all involves this very simple reaction, which is just taking two double bonds, putting them together in a new way. So here you see you split this and you put out two carbons and you make a ring. You take this and you spit out nothing, you just open a ring and make a polymer. So we'll talk a lot about that. And so we started out with catalysts that were totally ill-defined, and some of the early catalysts were ones we worked with based on titanium. And then Dick Schrock introduced tungsten and molybdenum catalyst, and then later we introduced the ruthenium catalyst. We sort of skipped over to ruthenium. And if you're not a chemist, it turns out that that titanium is over here on the periodic table, and then ruthenium moves to the right. And so as you move to the right, we get different catalysts. I'm really surprised that this reaction works with so many different metals. But the key is that olefins is what we want to react with. With this compound, we couldn't react with anything with olefins if there was anything else around. So these are all organic functional groups. And I think I don't have the slide to show that. But these are oxygens, mostly contain oxygens and nitrogens instead of carbons and hydrogens. So if there was anything else around, it wouldn't react. As we move across the periodic table, then when we get to ruthenium, it will react with olefins in the presence of lots of things, especially water. And water shows up everywhere. So it makes these catalysts really easy to use. And initially, these weren't so reactive, but then by changing ligands, and I hate to tell you, we're really going to spend a lot of time on ligands at the end. It'll be tough. But by changing that group to that group, we can make a catalyst which has same functional group tolerance, but is a lot more active. So this was called the second generation catalyst, and that's what really makes high activity. Okay, everybody with me? Okay.
You are still awake? You are still awake.
Still awake, okay, yeah. So, so here's the and so the other thing that we still like to do is to always try to understand the fundamentals of a reaction. All the details, try to understand which bonds are made and which bonds are broken in the process. So we can do this by doing all kinds of fundamental studies that, for President's sake, is that it costs lots of money and you've got to have lots and lots of good instruments to do this. And so that allows us to make these compounds, but they all have the same basic structure, two chlorines, a ruthenium, a carbon double bond with different groups. And so they all react by the same way. So for the inorganic chemists, if you count fast, this is a 16 electron species. It loses a ligand, makes a 14, adds an olefin, makes metallocycle, and around it goes. So it occurs just the same way as all the other mechanisms we've seen before. So we've got initiation, propagation, decomposition, and so these can all compete with the reaction. So we'll come back and talk about this later. Because in the end, what we want to do is to make better catalyst. And a more efficient catalyst means we get more turnovers, more things happen per metal center, and that's related to how fast this reaction goes, and decomposition stops it. So it's a ratio of those, which is what we really want to work for. So what we want to do is to design ligands which will give us fast propagations but slow decompositions. So that's the strategy. So we've done this with lots of different compounds, and so these are just ones we've made in our laboratory. You see they all have the same core, which is ruthenium, carbon, two chlorines, but then they have all kinds of different ligands on them. So this makes it water soluble, so we can do chemistry in water. So we're doing biological transformations with that. This is chiral, so we can do an anti-selective metathesis. We can make catalysts of a lot of different stabilities. And I'll show you this one later, which is a catalyst that's used in polymer chemistry. And the kinds of things you can do then is you can do ring closing chemistry to make rings. This is a standard reaction we'll talk a lot more about later. And there's lots of problems associated with this, which is the competition between making cycles and making polymers. And the problem is when you start to make hard cycles, this reaction rate goes down, and so you have to go to low concentrations to keep that ratio up, because that's what you want instead of that. So what we have to do then is to make run reactions in such a way that this is low concentration. So if that's low concentration, then this reaction is slow. When that reaction is slow, decomposition can take place. And so this causes lots of problems. So we need lots of better catalysts. The transformations are really sensitive. So the ratio of dimerization to ring closing, you see in this case, that's just a cycle. Here's just an open. This one gives all dimerization. This gives all cyclization. So it's very subtle things that make a difference in this. And so what we need are better catalysts that operate at high efficiency and high dilution. So it turns out that this ring closing reaction, I won't go through the details, is a reaction which is now being used in many places in industry. There are now pharmaceuticals that are in phase 2, finishing phase 2, and starting phase 3, which use this chemistry as a way of making the basic structure. And so it provides a very fast, efficient way of constructing very large molecules and very complex molecules. And so it's found lots of applications in the pharmaceutical industry. We're hoping soon, in the next few years, maybe a drug will finally make it which uses this chemistry as a way. And that'll be very exciting. Probably the first one will be a hepatitis C drug, because it turns out this is, they're very close. They had one drug that made it through phase 2. They found a little bit of toxicology problems. They've gone back and redesigned it, and it's coming through again, and so we think it'll make it. So that'll be exciting. So making fine chemicals is one area, and so the better the catalyst, the more things we can do. Here's another area which is of interest that's growing rapidly. So for the non-chemist, this is called biodiesel. Okay? So this comes from the saponification of soybean oil. It's called oleic acid. You see it's got a double bond. And so if we can do metathesis and change ends, and so if we break that and put these two ends together, we get that molecule. And if we put the other two ends together, we get that molecule. So this turns out to be a diester, so you can make polyesters out of that. This turns out to be lots of things you can use in many other cases. Okay? And this is a nice clean chemistry because there's no solvents involved. So there's no competing reaction, so we can go to very high concentrations. So this is a really clean reaction. And here's just one example of a self-metathesis of methyl oleate using one of the catalysts. You see we're operating at 5 parts per million, and the reaction's done in less than 10 minutes. So that's a couple 100,000 turnover frequencies, turnover numbers, turnover frequencies over 1 million. So these catalysts are now getting to the point where one can really start to do things on a very efficient way. And so this resulted in a collaboration between DOE, Department of Energy, and Cargill, which, and DOE knows Department of Energy. Cargill is a large private agricultural company. It used to be the largest privately owned company in the U.S., just got beat by someone else slightly. But they basically buy everybody's corn and soybeans. And a small company called Materia, which is a company I helped found to commercialize this technology. I'll be happy to talk about commercialization if you're interested. Caltech, which is my lab, so that's collaboration. DOE is interested because they want to replace petroleum-based products with those from renewable resources. Cargill's interested because they have a lot of vegetable oils, corn and soybeans, and the reason they're oils is because they have double bonds in them, CC double bonds. And if they have CC double bonds, then we can modify them by olefin metathesis. So after about 4 years of working on this project, mostly between Materia and Cargill, and I worked through Materia, is that a company was spun off between the two called Elevance. And so if you want to go on the web and look at This is a company that's about 6 months old now, which is very well funded. And basically what they're trying to do is to take these renewable resources and turn them into chemicals. And the advantage that you have is that if you try to make chemicals from hydrocarbons, from petroleum, is that you have to put in functionalities. So petroleum and is all hydrocarbons, CH bonds. So if you want to put in oxygen or nitrogen, you have to do a lot of chemistry. And that's usually very dirty and usually produces a lot of byproducts. So this chemistry now allows you to make things from biorenewables already functionalized, so now you can do simple chemistry to convert the one group into another one. So let's see what I put in here for this. Yeah, the first of the, this was a product that's going to pay the bills, and then we'll develop a lot of other things. And it's a very simple reaction, but it shows you the kinds of things you can do. So here's soybean oil. So it's a triester. It's got lots of double bonds in it. What Cargill had been doing for a long time is partially hydrogenating it. They're turning these double bonds into single bonds by adding hydrogen. And the more hydrogen you put in, the harder it gets. So if you want to make cooking, in the U.S. it's called Crisco, but it's a cooking material you partially hydrogenate. So everything is partially hydrogenated, because if you make it totally hydrogenated, it's too hard. But what happens in the process of hydrogenating the double bonds is some of the double bonds turn from cis, which is where they come out on the same side, to ones where they come out on opposite sides. So it's a very mechanical thing. And it turns out when you do that, these don't fit into membranes very well. They disrupt membranes because they have different shapes. And consequently, they're not good for you. And for example, in New York, trans acids, trans fats are totally banned, and a lot of other places. And so Cargill had a big problem. So they had all this hydrogenating capability, all this soybean oil. So they started hydrogenating completely to make a wax, which they call nature wax. It turns out it's not a great wax because it's too regular, and it's not high enough molecular weight. So what they found is that if they could throw in magic dust, they call it, which is our catalyst. I don't like that name after all the years we've worked on it. But it does metathesis. So it'll take that double bond and react with another one. So now you make a dimer, trimer, tetramers. So now it starts to increase the molecular weight. And then when you hydrogenate this, you end up getting a material which is a really good wax. And it's now being turned into a candle, which will soon be sold by Walmart, which is a little strange. But there's another interesting story behind this, is the reason this is valuable is not because it's cheaper and not because it's biorenewable. Nothing has made it yet as a biorenewable unless it's a better product. And the reason this is a better product is because people apparently buy candles for fragrance, not for light. So the more fragrance you can put in, the better the candle. And if you're a chemist, maybe not a chemist, is it turns out fragrances have lots of things in them other than carbon and hydrogen, lots of functionality. So you can't dissolve very much in petroleum, because petroleum is just CH bonds. There's a rule in organic chemistry is that like dissolves like. So you need functionality to dissolve functionality, and these have all these ester groups. So they make it very compatible with fragrances. So it turns out that these candles, you can dissolve a lot more fragrance in them, and so that makes them a better product. So all this chemistry used to make drugs, but it also can be used to make candles. And there's lots of other things that are making out of this now. So that's another direction we're going. So another area, and I thought I'd throw this one in for different from the talk this morning, is to talk about living polymerization. So this is another kind of way of stringing molecules together. So if you start with small molecules, that's called a monomer, and you put them together, it's called a polymer. So a polymer is made up of lots of little units. So if you have polyethylene, it's ethylene that's been strung together to make a polymer out of it. So you do it by starting with monomers, which we have A's, and turn them into these long chains. And there's a kind of polymerization where you start with an initiator, and it reacts with A, makes it active, that then reacts with another A, and this keeps growing until you make a big long chain. So the bigger the chain, the better the deal. And there's a special kind of polymerization for the polymer chemists and the chemists in the audience, which is called living. And it's a simple name because most polymerizations grow for a while and then the chain dies. It turns out in living polymerization, the chain grows and it stays alive. So it's called living polymerization. So you can grow the chain and stop. And if you have that special case, then you end up having the ability to control the molecular weight. That is, how many of the monomers you put together. And so the math is easy, especially for an engineer. It turns out that the number that you put together is just related to how many monomers you have relative to how many initiators you have. So if you have 100 monomers per each initiator, you get, on the average, a chain 100 long. Okay? So it's easy to control the molecular weight. And it turns out there's something else called polydispersity, which is related to the fact that when you grow a polymer, the chains grow in a random way. It's a random walk. And so you end up getting a distribution of molecular weights, which when you have a living system and everything is done right, is defined by a Poisson distribution. Okay? And that is if everything is controlled by statistics. And so we'll talk more about that in a moment. Okay? So let's go back to polymers again and our ruthenium catalyst. So if we start with this simple catalyst with two ligands, we know from our mechanism that we have to lose one of these to initiate. Once we make this can polymerize, react with many, many different monomers. It can terminate, but it turns out this is very slow. So that's okay. And so if this is the case, then we should be able to get narrow polydispersity if it's living, which this is. But the other thing we have to do is that all the chains have to start at the same time. Because if one catalyst starts and then another catalyst starts and another catalyst starts, things are not controlled by statistics. The only way they're controlled by statistics is if everything starts at the same time. Which means then that this reaction has to be fast relative to that one. The other analogy that I've heard is that it's like going to a racetrack. And so you put all the horses in the gate. All the gates open at the same time. The horses go around and they get a nice distribution, but usually unless you have one that's really bad, they end up in a nice distribution at the end. So that's what you want. And that's what happens if you have initiation fast relative to propagation. If you have a situation where the gate opens, another gate opens, another gate opens, then you end up with horses all over the track. So you need it living, okay? So when we started with our phosphine catalyst, it didn't work too well because we want this number to approach 1. But we found out ways of turning it into a catalyst where this number approached 1. But these were not very reactive and didn't react with, for the chemist, this would only react with exomonomers. And you make these by Diels-Alder, and Diels-Alder always gives you endo. So it was somewhat limited. But it turns out that the new ligand system would react with both. But it was too reactive, because now if we try to run the reaction, we end up getting a number above 2, which is really bad. We can play games and get it down a little better, but we could never get below 1.1, so we could never control this. So we were about to give up on ever being able to do good living polymerization with these systems until we went back and thought about it. We want this to be fast relative to that, so we need something that comes off faster. And we were making some complexes for another application, which were these that where we replaced the pyridine, the phosphors, the phosphines, with pyridines. And pyridines have nitrogens. And it turns out in these complexes, nitrogens bind very lightly to the ruthenium. So just enough to make it stable, but they come off very rapidly. So these come off about 1,000,000 times faster than if you have a phosphorus there. So this now gives us the very fast initiation, which is what we needed. And so then we could go to, and so we can put in pyridines. And, so this was the phosphine case. So you see initiation is really slow. When we go to pyridines, now it's really fast. So we can get the fast initiation. So now using these, we could make polymers with good relationship between molecular weight and monomer to catalyst ratios. We could get PDIs below 1.1. And for an application, which I probably should have put in, we made block polymers. And so the nice thing about a living system is you can grow, you use up the first monomer, and then you can put in a second monomer with different properties and grow a next one, and a third one and a fourth one. And so these are block polymers that we're growing and using to make micelles, which we turn into nanoparticles, which we're using to look at absorption of tumors by nanoparticles. So this is a whole nano area, but I put it in here just to show how well it works. You can see the PDIs are well below 1.1. Okay, we can control the molecular weights very precisely. Polydispersities are really low. So this system works out quite nicely. But there's a problem with a living system. You can get really good control, but it costs you a lot. Okay? Because you have one initiator and you grow, and at the end you kill it. And so you only get one polymer chain per initiator. Okay? And that's a big problem. So this is really technical stuff that we're just doing right now. So this is stuff that's really new. I just got the slides just before I left. So that's a problem. So can we figure out a way to be able to make more than one chain per metal center? And again, knowing all the chemistry, we can do that. So here's the thing that we wanted to do. So we took our bispyridine complex, we added our monomer, which is a strained double bond. Now we can make our living polymer. So this is a polymer, it has a ruthenium at the end, double bonded. And so then what John found, John Matson, who's doing this, is that he could add this molecule. You see, it's not a cycle. So now this cleaves, and when that cleaves, one part goes on to the end of the polymer, and the other part goes on to the ruthenium. Okay? So it now allows you to stop this with putting functional groups on. So that was good. And it turns out for the polymer chemists in the audience, so it's good polydispersity, it's good clean, approaching 1, good control. And then the other thing you can do for the polymer chemists is that this N group now, if you treat it with copper and a vinyl, does ATRP. So now you can grow a block onto it. So now we have a block that was grown by metathesis and then a block grown on by ATRP, and that makes a nice block polymer. And we can do lots of those. So now here was the solution to the problem, though. So if you think about it, whenever we grow our polymer, let's go back to that again. And so we grow our polymer, we add this, we make that. This turns out to be an active initiator. Okay? So that's a ruthenium carbon double bonded species. So that could react back with more again. So we end up having 3 kinds of double bonds in this system. We have the double bonds here, which are the most reactive. We have these double bonds, which are the second reactivity. And then we have the double bonds in the polymer, which are the least reactive. And they're least reactive because they have these bulky groups in the allylic positions. So they're blocked sterically. So what we can do then is just repeat this cycle. So we make this, we add the monomer, and then we add we have this around. And so when it finishes reacting with this, it then reacts with the less reactive double bond, cleaves off, makes the initiator, and then we can add some more monomer and start to grow again. So we can basically start growing many different chains if we do this right. And so this was done using a robot. I'll talk more about this a little later. This is a new toy for chemists, which is even more expensive than many tools you have. And I'll show you what it's used for a little later. And so basically, this is a robot that will add chemicals. And so we basically programmed this. So over 10 times, it added this. And so basically, it would add this, let it react for a few minutes, then add some more, then add some more, then add some more. So this is first, second, third, fourth, fifth. So you see the polydispersities are staying pretty narrow, and we're up to 10 chains per each initiator. So these catalysts then are the kinds of catalysts, by taking advantage of the relative reactivity and knowing the reactivity, we can make systems that actually cruise right along. So this was another we did, and so this is molecular weight. It creeps up a little bit because they're not immortal. The graduate student was really optimistic. If they were immortal, it'd stay straight across. And so a little bit of the catalyst dies every time, and so we're getting a creep in the molecular weight, and the polydispersity creeps a little bit. I think what we can do is that since we know how fast the catalyst is decomposing, we can program the computer so it'll just add slightly less monomer every time. So we'll be able to get these things really under control. So this is stuff that's new that we're just working on, and I thought I'd share it with the graduate students. So the next thing we want to do is make improved catalyst. So again, we got all the catalyst steps. We got initiation, we got propagation, we got death of catalyst. So we got to learn how to control all of those. Okay? So we want to control them, and we want to control stability. Okay, so that's the big deal. So to do that, we needed a way to evaluate catalysts rapidly, and so that's where this robot comes in. So it turns out that up till this stage, we'd make a new catalyst, and the graduate student would have to spend about 3 days on the NMR machine running spectra after spectrum after spectrum. And to get 3 days, it was normally the weekend, and the student working on this wife got very upset because every weekend he was gone most of the time running his things. And so it turns out that we had just bought this robot for doing catalyst discovery. It's made by a company called Simex, which is right down the road from Stanford. And so it's a big dry box, and then inside the dry box you can barely see it, but it turns out there are syringes that run back and forth, and they inject and squirt and do all kinds of things. And so you can mix up all kinds of chemicals with this. And so essentially what happens now is the student weighs his catalyst, takes it down, puts it in the box, spends about a half hour, programs the computer, then he goes away, he comes back the next day, takes his 96 well plates where the robot has carefully quenched all of his samples at the right times, puts it onto an automated GC, it goes through, it collects all the data, it comes back the next day, and it's done. So now we can evaluate things much, much faster, and so it's working out really well. So this happens while we're also discovering new catalysts. So this is funded by a grant that came from the Moore Foundation. And so Gordon Moore, who of the Moore's Law, was a PhD chemist from Caltech. So he's been very nice to Caltech. And so a few years ago, he gave Caltech $600 million, and $300 million of it went into special projects and special things. And so a little bit of it went here. Only a very small fraction of it went here. So at that stage, that was the largest amount of money ever given to a university in one stage. I think it's been beaten since then. So and so that's our Moore Center for Catalyst and Chemical Synthesis. And so I think sort of the next thing that's going to happen in chemistry is we're going to start using a lot more robots because it makes things a lot simpler to do. It takes the time that the students now spend washing dishes and shuffling things around and gives them time to go think and learn and do other stuff. So it works just as well as what we had done before on the bench. And the next thing you got to do is you can't have a system that's running so it gives 100%. If it gives 100%, you don't know whether you're getting better or not. So we then went through and started lowering the catalyst until we got to the point where we were below 50%. So at about 15 parts per million, we're now getting about 50% conversion. So we know if we're getting better or we know if we're getting worse. And so, so that tells us the same thing. So the next thing you want to do is you want to be able to find a reaction that's hard, a tough reaction, a reaction that will test your catalyst and test what you're going to do. And so this is a reaction that didn't work very well. So it's pushing really hard. The yield is quite low. It was done by someone else, but we've done it too. Moly catalyst worked pretty well, etc. And so this is sort of finishing off. And so the catalysts we used, the chemists will recognize that we have mesotyl groups here, which are methyls in those two positions. Those are one carbon fragments on both of those. And it turns out that those are essential to make a stable catalyst and to make a stable carbene. So these are called Arduino carbines, and Arduino found you had to have methyl groups to make them work. We had some hints from other chemistry that if we took those groups off, that we could open up some of the steric environment here and get a catalyst that worked a lot better. And sure enough, it did. So so these are our two standard catalysts. You see they don't work very well at all. This is a catalyst where now you see we've taken a methyl group and we've made it bigger and moved it back here. So that works pretty well. This one we were able to take off all of the groups, and that works pretty well for this reaction. So this idea of removing methyl groups starts to work, but it costs you something. And remember, I talked before about we're always doing the battle between propagation and decomposition. And so if we warm this catalyst, it decomposes and makes this compound. So you see that compound has the benzyl group attached to the ortho position. We have crystal structures of those. And the easiest way to think about it is this mechanism. So you see what happens is that we have an electrocyclic reaction. So 6 pi electrons forms a ring. This then hydrogen can transfer over and then reductively eliminate, and you make the product. Okay, so that's the transformation. And if you think about this, what's happening in this overall transformation is that ring has to become coplanar. And so we think what had happened before with the methyl groups is that those methyl groups prevented it from becoming coplanar, and even if it did interact, breaking a carbon-carbon bond is a lot harder than breaking a CH bond. So the methyl groups help protect this and make a much more stable system. So that happens in a lot of cases. A lot of phosphines are involved. So we made a compound with one less methyl group. I was surprised we could make it, but we could. We continue to get surprises in this area. And when we cool, we can see 2 signals in the NMR, and it's hard to see the things down here, but it turns out these are way downfield. One of the joys of working with these is this CH bond shows up downfield away from everything. So when you cool it down, you can see 2 signals. One we know is this, the other is the methyl groups on opposite sides. So the same side and opposite sides. This turns out to be the major, which was a big surprise. But as we warm this, they become equivalent. And so by looking at NMRs, you can measure rates of rotation relative to the lifetime of the NMR signal. And so this tells us then that these things are rotating. And for this to rotate, it has to become coplanar. And so that gives us the maximum energy, the transition state, for going from there to there. So we can measure that by this rotation, and that's about 14 kilocalories per mole. So this turns out to work. It gives a really nice catalyst for this tetrasubstituted double bond. Much better than anything we'd seen before. And it allows us to do lots of tetrasubstituted double bonds. And so it's now becoming a reaction that the organic chemists are taking over and using in lots of places. And so we thought we knew what we were doing. So we said, okay, steric bulk causes problems. And so we had studied before these cross metathesis reactions where you put those together, you make ethylene, and you couple these together. And we'd observed under conditions where we could normally get good yields that if we had a lot of steric bulk in the allylic position, the yields would drop. So here's the green catalyst, and so here's the yields, and they're less than what we would like. So we said, okay, this has steric bulk, so maybe if we remove part of the steric bulk, we can get the reaction to go better. So sure enough, when we used this, we got over 90% yields in all cases. So looked like we knew what we were doing. So we pushed it to the next level. We said, okay, let's now go to making tri-substituted double bonds, which have been troubles in the past. So some of these are quite low. So this is starting with vinyl cyclohexene and the corresponding terminal olefin. You see that's 78%. When we used the new catalyst, instead of the yields going up as we hoped, the yields went down. So we obviously didn't understand what we were doing. So we thought about it some more, and we thought about when you do cross metathesis, you've got an added wrinkle. So when you do ring closing, R's are tied together, and you can't do anything except productive metathesis. When R's are not tied together, you can turn it this way or you can turn it that way. When you turn it that way, now you make the 4-membered ring. Now, no matter which way you cleave, you still get back an R group. And so all you do is just exchange methylenes. You don't do anything productive. So what we thought might be happening then is that by putting 2 R groups in these 2 positions, we were controlling the ratio of productive versus non-productive. And so this is non-productive here, where the R groups are in the 1,3 position. This is the productive. So this now is the case where we have open space, and this is the case where we have a methyl group which will bump into the R group. So the proposal then was that in these catalysts is that we had more productive metathesis than in these, where it could go to the non-productive route. So I called up the student after seeing this and said, if taking away steric bulk is bad, let's add steric bulk. So we had a more bulky catalyst in the lab, which is this red one, where we have isopropyl groups here. Look what happens. Yields jump up to 98 and 96. So again, thinking about mechanisms, thinking about how the reactions take place, allow you now to start to go back and make very subtle changes which show up as significant changes in the overall process. So and so one methyl group is almost enough, but we still find a problem. If you heat this, you end up with a crystal structure like this. You see again, we've inserted into the ortho position. We think again this thing goes coplanar and inserts and makes the ring. So we got to make it even higher. So we need to prevent that rotation. And so what we thought, so one methyl group's almost enough. So when it turns flat that way, the methyl group bumps into the backbone. When it turns this way, the methyl group sticks down. So that's the reason this catalyst works at all. But we wanted to make this even worse. So we said, okay, let's put methyl groups on the backbone. So if we take the methyl groups from there, put them on the backbone, now we've opened up the catalyst center, which gives us much faster propagations, but maybe these will prevent the decomposition and give us a stable catalyst. So we'll win in two ways. We'll win in propagation, we'll win in decomposition. So we made it. It turned out to be pretty simple after we learned, as it usually is. It's a Grignard addition to these things making the carbene. And again, if you don't have methyl groups on the backbone, you can't make this carbene. It dimerizes. So these methyl groups apparently hold these phenyl groups, so this can't dimerize. So once we make it, we can put it on the metal, and then we're off and running. Here's the crystal structure again, so we know what it looks like. And we do our experiment again, so we make the one with methyl groups on it. We look downfield, so you see between 16 and 17. We see two signals, which we know are the two signals here, which have the methyl groups on the same side and opposite sides. We don't know which is which. Now at room temperature, they're separated. We heat them to 75 degrees, and they're still separated, which means they're not rotating. So we can do simple calculations from that and show that the barrier for this rotation is at least greater than 21 kilocalories per mole. And remember, one without the methyl groups was about 14. So we've raised this barrier significantly, which should raise the barrier for decomposition by this CH activation mode. And sure enough, it works. So here's our difficult reaction. It works really well compared to everything else we've made before. We can stabilize things that weren't stable before, so this compound decomposed rapidly. We put two methyl groups there. Now it's stable for days. Prevents this, again, this rotation, this electrocyclic reaction. And it works for all kinds of mesotels, making really stable catalyst. And the key one, I think, is the next one. Yeah. So this is go back to the methyl oleate again, doing this dimerization self-metathesis. This reaction goes very cleanly again. Now the turnover numbers are almost 500,000. So that means we can do this reaction now with 2 parts per million catalyst. So we're getting to the point where the amount of catalyst we have to put in is insignificant. So the cost and everything else doesn't matter. So that's really what we're driving for. But I hope you can see that in the process of trying to solve some of these very practical problems, we have a chance to do lots and lots of really fun fundamental chemistry, measuring rate constants, looking at all kinds of good organometallic chemistry. So that's really what we want to do. Once this is done, we're finished with it. But the guys in industry are very interested, so they take it off and go running and do a lot of other things. So that's how the chemistry goes these days. So yeah, and so the second generation was 200,000. Now we're up to about 500,000. Okay? So I went through a little fast, but it was a lot of details. And so I've had a lot of phenomenal students over the years. I'm up to about probably 230 or 40 students and postdocs who have worked in my lab. This is the present group. It's about 20 people. There's a few more because there's a few odds and ends of people who are coming and going. But the other fun thing, too, is that I have people from all over the world showing up. Unfortunately, I haven't had too many people from Taiwan in the last few years. Not as many are coming to America. But just to give an idea, so Chol is the one who did the chemistry I talked about last. He's a postdoc from Korea, got his PhD at Stanford with Barry Trost. He's from Switzerland. She was born in China but grew up in the U.S. He's from Chile. He's from Japan. He's from China. He's from France. He's from Kazakhstan. He's an undergraduate. First undergraduate I think we've had from there. She's from Canada. I think she was born in Canada. And then she's from Russia. So that's just the sort of present mix of people in the group that come, and they all add to the chemistry. And so Cho Chang is the key person on the end things. Ian Stewart did a lot of the intermediate chemistry, which I talked about, and most of the chemistry of those two. J.B. Borg has contributed. Oh, and Kevin is the one who now does the robot and gets to stay home occasionally on the weekends rather than spending his time on the NMR machines. Okay, good. Thanks.
For questions. Any questions from the audience?
For the polymer chemistry, let's say the monomer is living. Okay, so this batch will blend together, and then when they precipitate from the solution, then they are dead.
Yeah.
Okay, but for the living polymerization, it seems it didn't have this fact.
Yeah,
But
right. So they
what's
stay
the reason?
They stay in solution. We use the right solvent so they don't precipitate.
But eventually they will,
Yeah, but
right?
we don't make them that big.
Oh,
And so these would have to be millions and millions of molecular weight to precipitate.
okay. So what type of solvent is so strong? Or you can you got to pick the
Yeah,
monomer
we
or
can
something.
choose things. Yeah, we can choose things. Yeah.
Oh, okay.
So yeah.
No surprising. This lady is the chairman of Department of Chemistry.
Okay, okay.
She always gives us a hard
Okay,
time.
okay.
Okay. Okay. Any other questions? 同学有没有什么问题？如果英文不行的话，我帮你翻译。Okay.
Should have some questions from the students.
Yes.
I see them all sinking
Yeah, the
down.
president has a question. Definitely, he's not a chemist. Okay.
Okay, yeah.
He enjoys your dancing picture.
Well, at least I understand a little bit. You turn the soybean oil into the wax.
Okay,
Okay. Is that really cheap that way in a sense? Well, you know, wax can be from different sources.
They seem to think so.
Okay.
And so now wax comes from petroleum. And petroleum prices are going very, very high.
Okay.
And apparently there's shortage. So this is competing. So it's the cost, but it's also the property that you can put more fragrance in.
Okay. Pretty much that's the only thing I understand in your talk. But you talk a little bit about the random walk and then Poisson distribution. Could you elaborate a little bit about that? So I do a little bit of statistics,
Okay.
sort of things.
Yeah. And
Okay.
so the and so it turns out polymerization, especially in the U.S. for a long time, was all physical chemistry. So there's lots of physical polymer chemistry. And so the whole idea of living polymers and molecular weight distribution, I assume Florey had something to do with it. Florey had something to do with everything. But basically, as you start a chain growing, it can either, and so basically some chains grow, and so the growth of a chain is just a random walk. And so you end up then at the end with a molecular weight distribution, which is just controlled by the random walk.
So the time derivative of random walk becomes Brownian motion.
Okay, yeah.
So
Yeah.
integrate the Brownian motion.
Okay.
The time derivative of a random walk become a Brownian motion.
Okay.
That's my understand.
Okay.
So your discussion is something certainly related to back to the Brownian motion. Is that?
Probably it's just,
okay.
just the encounter of a growing chain with a monomer.
Okay.
Yeah.
Okay. Anyway, thank you.
Excellent questions from a non-chemist. Okay. Great. It's really impressive.
I thought I would say, Poisson distribution. That's about, yeah.
Okay. So you have very wonderful skill to communicate with non-chemists.
Okay.
Okay. Any other questions?
Yes. Okay. Yeah, we've made complexes with almost every other metal, and the only other thing that works sort of is osmium, and it's a lot more expensive and a lot more toxic. And ruthenium, for example, if you make a ruthenium carbon double bond and add an olefin, it makes cyclopropanes. It doesn't do metathesis. So I don't know why ruthenium is there. That's for the theoreticians. We found it sort of by accident and built from there. So we've tried everything else. So we started out with titanium and marched our way across the periodic table. And I always tell the joke that, that I had an old colleague, Bob Ireland, who was very conservative. And he was always upset at me because I didn't agree with him on anything. And so he always told me that I would move to the right as I got older and had more money. So I haven't done it politically, but I have chemically moved from titanium to ruthenium.
Great. Okay. I have a tough question. Okay. Would you back to a couple slides to get any picture of the catalyst?
Okay.
Back one more. We need to. One more. Okay.
Okay, that one?
Okay.
Yeah.
This functional group
Yeah.
is called the MNL.
Okay, yep.
Right.
Yeah.
MNL in general is not stable.
Okay, yep.
So when it's attached to ruthenium, then you use this catalyst very well.
Yeah, right.
I'm just curious about, because this part is not stable, I don't know.
Yeah.
After you attach this to ruthenium, what will happen?
Yep.
Will this catalyst stable or something?
Oh, yeah.
Oh,
Yeah, it's very stable. You can make it and put it in there. So here's the chemistry that is used to make them. So you make these salts,
yes.
okay, and then you treat them with a strong base, and you pull off the proton, and so it's neutral then, and so it's a carbene. So
Okay.
it's stabilized carbene, and so the lone pairs of electrons are donated into the empty p orbital of the carbene to stabilize it. So this is not super stable. It will react with oxygen and water, but when you put it onto the metal, then it's stable.
It's wonderful.
Yeah. then it's
Okay,
wonderful.
that's amazing. Okay.
Yeah.
The next question is,
Yeah.
based on your design,
Yeah.
you have, okay, just this way, okay.
Yeah.
You have nitrogen here,
Yeah.
nitrogen here.
Yeah.
Nitrogen, this group will be back and forth, right? It's flexible.
No, that's planar.
It's pretty fixed?
Yeah, it's pretty fixed planar. It can rotate, but it can't go
But
back
it's,
and forth so
okay.
much. Yep.
So this is the reason you put the MNL there.
That's right, yeah.
With the
Yep.
ruthenium. Okay,
Right,
that's
yeah,
very
yeah.
nice design. Okay.
Yep.
Okay, great.
Okay.
Okay, any other questions from the students especially?
Students.
同学有没有什么问题?
And so about anything. I'll answer questions about anything.
Yeah, anything. How did you get a Nobel Prize? Right? How hard it has to work? Maybe 25 hours per day only? Okay. Any questions from faculty members?
He looks young enough to be.
From the RCM, it look like you got two kinds of explanation. One is ring cross metathesis. The other one is ring cross metathesis. So I was curious, when you have a double bond and then you mix them together, somehow the double bond is flying away and you got two double bonds there. How do you know it's going to form which RCM? Is it going to form cross, and so you current the rim, and also, but the other way is you're going to form the polymer. So how can you control it?
Well, it's controlled by the ring strain. So it's so if you have a very strained ring, you're almost always going to make polymer. But if I can find this back at the beginning. Yeah, here we go. So if you have a strained ring, then that reaction will be slow. If that reaction is slow, then that reaction takes over. So what you have to do is to go to more and more dilute solutions. So the more dilute you make it, the more cycle you get. In polymer chemistry terms, there's a critical concentration, and so you have to be below the critical concentration to be able to get cycles. If you're above it, then you make polymer. And the critical concentration depends on the ring strain. So for example, norbornene, that goes completely to polymer. You cannot take it back to norbornene again because 25 kilocalories per mole. Okay? So you have to be able to control the reaction by just concentration. And some rings you can't close. We fail in many cases.
So basically it could be controlled by adjust the concentration of the solution.
Yeah, right.
It's
Yeah,
okay.
right. Mostly, yeah.
And then the other question I want to ask is the black copolymer that we make is quite different from our idea. Normally, our copolymer that we try to make is one size homogeneous, and then the other size it kind of like a two black of a copolymer. But in your robot system, you can make a polymer like pretty fancy. It's one black and then the other one and then the other one.
Yeah.
So I was curious, what's the special function for any of your new polymers?
So those are made for, and I should have done it. If I'd known the audience was going to be quite this general, I would have put that in. Come on. This is hard doing things in front of people, especially when you're tall. Of course. Yeah. So the reason I use an Apple is because whenever ChemDraw came out, it was on Macintosh. And the other thing is that Apple is multiple choice. PCs, you had to remember things. And I like multiple choice.
I use Apple as well.
Yeah. So let's see. Is that it? Yeah. Yeah. So here's what we're doing with the. Nope. That's the drug that's being used for hepatitis C. Yeah.
这是那个 C 型肝炎的药。Hepatitis C has no drugs at this moment, right? Okay. C 型肝炎现在没有，市面上没有药可以治 C 型肝炎啊。他发明了一个 C 型肝炎的药。OK。
So these are lots. So that's lots of. So this is what these polymers are being used for. So it turns out there's when tumors grow, they grow their own blood vessels, so they can grow rapidly and spread. And so it turns out when they grow rapidly, the blood vessels they grow are called leaky. They're not very good. The epithelial layer is not very good. And so it turns out they will let macromolecules through more rapidly than healthy tissue, which has a really good epithelial cells. So the proposal then is that you can make nanoparticles of exactly the right size, and they will go into tumors, but they won't go into natural normal tissue. Okay? And so so what we're making now are nanoparticles where we use our chemistry to make hydrophobic, hydrophilic. We then put them into water, they make micelles, and then we cross-link them, so now we make nanoparticles. Okay? So that's the reason we did it. Here's the slide I showed you before. That's for cross-linking. That's for putting F18 in. And so we've made a lot of these. And this gives you an idea. So now these are very small nanoparticles. These are very large nanoparticles. So we can make them using this technology. And so then what we're going to do is put F18 in, and then we feed them to rats that have tumors. And then we can do kinetics on the uptake as a function of size. And so once we know exactly what the size we need, then we can start to design therapeutics.
That the hepatitis C drugs was synthesized in your group?
No.
No, okay, developed by
It was made by Bertel Ingelheim.
I see. I tell you the experience of my group.
Yeah.
We used to have SARS to hit us about 3 years ago.
Right.
Okay, so our country dumped lots of money to make the compounds for anti-hepatitis C. Okay. So we made a lot of compounds. Yeah. After screening by Professor de Clark in Riga Institute, none of them is active. Okay. Then he sent me a letter that those compounds, some are very active against hepatitis C. Okay. So it turns to be more useful. Okay. That's our experience. Okay.
Yeah. No. So these are made by an interesting way. So this is a new way to design drugs. So this is a peptide, and so enzymes are peptides, and so you make a peptide which has the right functionalities, and then you put on straps. So these are hydrocarbon chains, and then by changing, so it's modular. And so they go to make a whole family of these by changing the size of these arms. Then they ring close and make a ring, and the ring sets the conformation of the peptide piece. So by controlling that, then you can control the activity of the system. So here's the drug down here that was made.
So this step involves 400 kilograms.
They've made 400 kilograms.
Very, very successful. Huh?
Yeah, yeah.
Okay.
I was surprised, yeah.
Yeah,
Especially
great.
since it has to be done dilute.
That's right. 50 member rings is very difficult. 这中型的 ring 不容易做，
Yeah.
在化学上面。Any other questions from students? Students, wake up. Huh? Oh yes,
Yeah.
non-chemist. Let's see
Non-chemist, yeah, I know.
how much he learned.
I ask a student, a question for a student. I think they all want to know, to ask you how to become a good scientist. Can you say a few words of wisdom?
Yeah, maybe. I mean, first of all, as I tried to show you, we started working on this just because we were excited and it was fun. We didn't decide we were going to go make a reaction that would be used in industry to make hepatitis C drugs or to win a Nobel Prize or anything. We started working on it because it was fun. It was an exciting, interesting project. And then you follow it and you work really hard. And if you're lucky, it'll lead you someplace. But the key is to find something that you're really excited about. If you're not excited, it's going to be a really hard life. Yep. You get it? Yep. Yeah, right.
Second, you have to be very excited.
Yes.
Yeah. Third, you have to be a good lecturer, okay, to present your chemistry. Okay, let those non-chemists understand what he is doing. Yeah. Our guest, do you have any question? No? Okay. You, okay.
Yeah.
Be careful.
I was wonder, the black copolymer, they can, through some kind of process to make some nanostructure,
Right.
well defined. I always wonder, have you planned to design some new black copolymer? You say you're a catalyst, so sure. And to predict after those black copolymer, after process, they have all kind of size, all kind of structure, something like that?
Yeah. Not so much. I mean, so far we're just stopping with the easy thing. And so this is a situation where when you put it in water, the hydrophilic part stays on the outside and the hydrophobic in the middle. So now we've designed this so we know what size this will be. Okay? So that's the easy one. Now the next is going to the next scale, which is getting big parts with nanostructures and everything else. I'm leaving that for the next generation.
How many nanometers of this polymer? Those can be separated, right? If we want, right?
Well, what we do is, I skipped over that. So what we put in is a...
What's the core?
Photocore. So this group.
Oh,
so when we
okay.
photolyze, it dimerizes.
Oh, I see.
And that cross-links. So it holds it all together.
Yes, great.
Okay? It takes only 3 minutes.
3 minutes.
And it's done.
Okay, great. 同学还没有问题？
More questions?
Any questions from the students?
I've had lots of questions from students in the past. So.
Yeah, they are very serious. 对对，我帮你翻译。有没有什么问题？来，this lady.
Okay.
I want to know how you plan your life. Just do what you want to do, or you have decided everything.
Oh, okay. Oh.
She's only 16.
16, okay. Oh,
You're 66, okay. She wants to know how to plan the life.
Yeah, so, well, if you ask my wife, she'll tell you I never plan anything. I follow my intuition, and as you see, we start to do one thing, and that doesn't work, but it gives us a result. We go follow the next thing. So we just bounce around from following the easiest path and see where it takes us. And so that's really the fun part of research, is that you can follow things as they develop. You don't wake up and know tomorrow you're going to have a result. In fact, I make a joke about, I used to have a colleague who is in another area where you have to plan things very carefully. And we would interview candidates, and his favorite question was, well, what are you going to be doing in 5 years? And when he asked that question, the candidate was dead. Because if he couldn't tell him what he was going to do in 5 years, he was upset. if he could tell me what he was going to do in 5 years, I was upset. Because I think, you have to be able to go in many directions. Okay?
Just recall the time when you were, say, 15, okay? You think about it, you're 15, okay? Do you expect what you are doing?
Oh, no.
In 30, okay? Then 40, then 50, never, right?
Well, things start to get to be a little more predictable. But at 15, I wasn't even sure I would go to college.
You do at that time.
And when I did, I thought I was going to major in agriculture. Go back and teach farmers how to grow things back in Kentucky.
Apple? To grow apples?
Well, apples or whatever, yeah, tobacco.
Okay.
Tobacco.
Tobacco?
Yeah.
Okay. Then you should go to Cuba.
Kentucky grows very good tobacco.
Oh, really? Okay.
Yeah, That's how I paid part of my way through college, was working in tobacco fields.
That's very rewarding, right? What do you plant? What do you get?
Oh, yeah.
Yeah, for chemistry reactions, no.
Oh, chemistry,
9 of the 10s in the field.
You mix things together and you get solid out. It's nice.
That's polymer. That's black tar. It's called a polymer.
No. Nice, beautiful crystals.
Okay.
Sometimes when you plant things, they don't grow either. So, or it doesn't rain, or the sun doesn't shine. So there's lots of problems there as well.
What happened to you when you were 15? You doesn't want your wife know that, right?
I don't remember when I was 15.
And then my question is, when did you meet your wife?
I met my wife in graduate school.
Graduate school.
Yeah, at a dance.
Okay. At a dance?
Yeah.
Okay, wonderful. Wonderful.
that
Very
was-
romantic.
That was 41 years ago.
41 years. Okay. Great. Okay. Okay, if no more questions, you do, yeah.
Global warming, yeah. Well, chemists had a lot to do with it, so we have to do a lot to help solve it. And, I don't know. And so one thing we need to do is change the processes we're using so they're a lot greener, so there's less byproducts being formed, a lot more CO2, a lot less CO2. I think a lot of chemists need to get involved in developing better solar devices and developing better ways of converting coal and other things into products. I'm hoping that this trick of converting biorenewables into chemicals will be a useful way to help solve that. But chemists have to be involved, and I think we are, hopefully, starting to be involved. And we're going to have to be a lot more.
Then how do you view these days about the energy wasted by people?
Energy waste
by Americans.
By Americans, I know. Yeah, I'm very unhappy with my neighbors who drive Hummers. So a year ago, I bought a Prius, the hybrid car, which works really well. And so I'm hoping, and so what's happening very rapidly is if you want to buy an SUV in the U.S. now, you can buy one very cheap. Yeah. So they're not selling anymore because gas prices are so high that people are now buying cheaper, smaller cars that are more efficient. So that's what's going to drive it.
Chemists should jump into this field to do lots of works on energy saving, you think?
Well, one of the places where I think chemists can help in the energy area also is in batteries. Yeah, because one of the big parts of the energy thing is going to be storage. And so we need much better rechargeable batteries. So if we had light rechargeable batteries now, we could have electric motor scooters, electric cars. So it's the battery technology which is really what's doing it. And that's a lot of chemistry, a lot of engineering, lots of things together. Yeah.
Great. If there is no more questions, please join me to give Professor Robert Grubbs a big applause. Okay. Thank you very much.